Artificial intelligence, or AI, is rapidly changing the world as we know it. From self-driving cars to personalized medicine, AI is poised to revolutionize countless industries. At its core, AI empowers machines to learn from experience, adapt to new information, and perform tasks that typically require human intelligence. This transformative technology is no longer a futuristic concept. It's here, it's evolving, and it's shaping the future. While both machine learning and deep learning fall under the umbrella of AI, they differ in their approaches, strengths, and ideal use cases. Machine learning algorithms are generally well-suited for tasks involving structured data, such as predicting customer churn based on purchase history or detecting fraudulent transactions in financial systems. These algorithms often require more human intervention in terms of feature engineering, which involves selecting and transforming relevant data features to improve model accuracy. Deep learning, with its ability to automatically extract features from raw data, excels in domains characterized by unstructured data. Image recognition, for instance, benefits significantly from deep learning's capacity to analyze pixels and identify objects, faces, and scenes without explicit instructions. Similarly, natural language processing tasks, such as machine translation and sentiment analysis, rely on deep learning to decipher the complexities of human language. Machine learning, a cornerstone of modern artificial intelligence, empowers computers to learn and improve from experience without explicit programming. Imagine teaching a child to recognize a cat. Instead of providing a rigid definition, you show them numerous pictures of cats. Over time, the child learns to identify the distinctive features of a cat, its pointed ears, whiskers, and tail, and can differentiate it from other animals. Similarly, machine learning algorithms learn from data, identifying patterns and relationships that enable them to make predictions or decisions on new, unseen data. These algorithms don't rely on pre-programmed rules. Instead, they build their knowledge through a process of iterative learning, refining their understanding with each new data point encountered. This data-driven approach to problem-solving has far-reaching implications, revolutionizing industries ranging from healthcare to finance. Machine learning enables computers to analyze vast data sets, identifying subtle trends and anomalies that would be impossible for humans to detect manually. This ability to extract meaningful insights from data fuels innovation and drives progress across countless domains. Supervised learning, the most prevalent type of machine learning, operates akin to a student learning under the guidance of a teacher. In this scenario, the algorithm receives a dataset where each data point is labeled with the correct output or answer. The algorithm's task is to learn the mapping between the input features and the corresponding labels, enabling it to predict the output for new, unseen data. Consider a scenario where you want to build a model that predicts house prices. In supervised learning, you would train the algorithm on a dataset containing information about various houses, including their size, location, number of bedrooms, and most importantly, their actual sale prices. The algorithm would then learn the relationship between these features and the target variable house price, allowing it to estimate the price of a new house based on its characteristics. Supervised learning finds applications in numerous domains, including spam filtering, medical diagnosis, and credit risk assessment. For instance, email providers use supervised learning to classify incoming emails as spam or not spam based on features like sender address, content keywords, and email structure. By training on a labeled dataset of spam and non-spam emails, the algorithm learns to distinguish between the two, protecting users from unwanted messages. Within supervised learning, there are two main categories: classification and regression. Classification deals with predicting categorical outputs, such as whether an email is spam or not spam, while regression focuses on predicting continuous outputs, such as the price of a house. Both approaches play crucial roles in solving a wide range of real-world problems. Unsupervised learning, in contrast to its supervised counterpart, delves into the realm of unlabeled data, seeking to uncover hidden patterns, structures, and relationships without explicit guidance. Imagine a detective piecing together clues from a crime scene without knowing the identity of the perpetrator. Unsupervised learning algorithms operate similarly, extracting meaningful insights from data without predefined labels or targets. One of the most common applications of unsupervised learning is clustering, where the algorithm groups similar data points together based on their inherent characteristics. For instance, a music streaming service might use clustering to segment its users based on their listening habits, creating personalized playlists and recommendations tailored to individual preferences. Another prominent use case is dimensionality reduction, where the algorithm aims to reduce the number of variables or features in a dataset while preserving its essential information. This technique proves particularly useful when dealing with high-dimensional data, such as images or text, where reducing the number of features can improve computational efficiency and model performance. Unsupervised learning plays a crucial role in exploratory data analysis, anomaly detection, and recommender systems. Its ability to uncover hidden patterns in data makes it a powerful tool for businesses seeking to gain a deeper understanding of their customers, identify potential risks, and optimize their operations. Reinforcement learning, or RL, takes inspiration from behavioral psychology, enabling machines to learn through trial and error, much like how animals learn to navigate their environment. In RL, an agent interacts with an environment, taking actions and receiving feedback in the form of rewards or penalties based on its choices. Imagine training a dog to fetch a ball. You reward the dog with praise or treats when it successfully retrieves the ball and provide negative reinforcement when it fails to do so. Over time, the dog learns to associate the action of fetching the ball with positive rewards, increasing the likelihood of repeating the desired behavior. Similarly, in RL, the agent's goal is to learn a policy, a set of rules or strategies, that maximizes its cumulative reward over time. The agent explores its environment, experimenting with different actions and observing the consequences, gradually refining its policy to achieve optimal performance. RL finds applications in robotics, game playing, and control systems. For instance, self-driving cars leverage RL to navigate complex traffic scenarios, learning from their mistakes and improving their driving skills over time. The rewards in this case could be positive for safe and efficient driving, and negative for collisions or traffic violations. Deep learning, a specialized branch of machine learning, has emerged as a transformative force in artificial intelligence, enabling machines to achieve unprecedented levels of accuracy and sophistication in tasks once considered the exclusive domain of human cognition. At the heart of deep learning lie artificial neural networks, complex structures inspired by the intricate network of neurons in the human brain. These networks, composed of interconnected nodes organized in layers, process information in a hierarchical manner, extracting increasingly abstract features as data flows through the network. Unlike traditional machine learning algorithms, which often require human intervention to select and engineer relevant features, deep learning algorithms excel at automatically learning representations from raw data. This ability to extract meaningful features without explicit programming is what sets deep learning apart, allowing it to tackle complex problems involving unstructured data, such as images, audio, and text, with remarkable accuracy. The deep in deep learning refers to the multiple layers of interconnected nodes that constitute these networks. Each layer performs a series of computations, transforming the input data into a more abstract representation that captures higher-level features and patterns. This hierarchical processing allows deep learning models to learn intricate relationships within data, enabling them to make accurate predictions or decisions even in the face of noise, variability, and complexity. Deep learning's ability to learn from vast amounts of data, coupled with its capacity for automatic feature extraction, has revolutionized fields such as computer vision, natural language processing, and robotics, paving the way for groundbreaking applications that were once considered the realm of science fiction. To understand the power of deep learning, it's essential to delve into the structure of artificial neural networks, the computational building blocks that underpin this transformative technology. Imagine a vast network of interconnected neurons, each responsible for processing and transmitting information. Artificial neural networks, inspired by their biological counterparts, consist of interconnected nodes, organized in layers mimicking the structure and function of the human brain. A typical neural network comprises three types of layers: an input layer, one or more hidden layers, and an output layer. The input layer receives the raw data such as pixels in an image or words in a sentence. Each node in the input layer represents a specific feature of the input data. These nodes then pass the information to the hidden layers where the magic of deep learning unfolds. Hidden layers, the heart of a deep neural network, perform complex computations extracting increasingly abstract features from the input data. Each node in a hidden layer receives input from multiple nodes. In the previous layer applies weights to these inputs, sums them up, and then passes the result through an activation function, which introduces non-linearity and allows the network to learn complex patterns. The output layer, the final layer in the network, produces the final prediction or decision. The number of nodes in the output layer depends on the nature of the task. For instance, a network designed for image classification might have one output node for each possible class, while a network for predicting a continuous value such as house price would have a single output node. Deep learning's ability to process vast amounts of data, automatically extract meaningful features, and learn complex patterns has fueled a revolution in artificial intelligence, enabling machines to perform tasks once thought to be the exclusive domain of human intelligence. From image recognition to natural language processing, deep learning is transforming industries and shaping the future of technology in profound ways. One of the most remarkable applications of deep learning is in the field of computer vision, where it has achieved superhuman accuracy in tasks such as image classification, object detection, and facial recognition. Deep convolutional neural networks, specifically designed for processing visual data, have proven exceptionally adept at analyzing images, identifying objects, and even understanding scenes. In natural language processing, deep learning has enabled machines to comprehend and generate human language with unprecedented fluency and accuracy. Recurrent neural networks, particularly well-suited for processing sequential data like text and speech, have revolutionized tasks such as machine translation, sentiment analysis, and chatbot development. Deep learning's impact extends far beyond these examples, permeating fields such as robotics, finance, healthcare, and more. Self-driving cars rely on deep learning to navigate complex environments. Financial institutions use it to detect fraud and predict market trends, and healthcare providers leverage it to diagnose diseases and develop personalized treatments. The possibilities of deep learning are seemingly limitless, with new applications emerging all the time. Deep learning, with its remarkable ability to learn from data and make intelligent decisions, is rapidly transforming industries and shaping the future of technology in profound ways. Its impact is being felt across a wide range of sectors, from healthcare and finance to transportation and entertainment, revolutionizing the way we live, work, and interact with the world around us. In healthcare, deep learning is playing a pivotal role in improving patient outcomes, from early disease detection and diagnosis to personalized treatment plans and drug discovery. Deep learning algorithms can analyze medical images such as X-rays, kinetic scans, and MRIs, with remarkable accuracy, assisting doctors in identifying anomalies and making more informed diagnoses. The financial industry is also undergoing a deep learning revolution, with applications ranging from fraud detection and risk assessment to algorithmic trading and customer service automation. Deep learning models can analyze vast amounts of financial data, identify patterns and anomalies, and make predictions about market movements, helping financial institutions make better decisions and mitigate risks. As deep learning technology continues to advance, we can expect even more transformative applications to emerge, further blurring the lines between human and artificial intelligence. From personalized learning experiences and intelligent assistants to self-driving cars and smart cities, the future of deep learning is brimming with possibilities, promising a world where machines augment human capabilities and solve some of society's most pressing challenges. One of the most fundamental distinctions between machine learning and deep learning lies in their appetite for data. Machine learning algorithms, while capable of learning from data, typically thrive on structured datasets of moderate size. Think of them as discerning eaters, capable of extracting valuable insights from a well-prepared meal but easily overwhelmed by an excessive buffet. Deep learning algorithms, on the other hand, are voracious consumers of information, requiring massive datasets to unleash their full potential. Imagine them as data-hungry giants capable of devouring mountains of raw information and emerging with a nuanced understanding of complex patterns. This difference in data dependency stems from the inherent nature of their learning processes. Machine learning algorithms often rely on human experts to select and engineer relevant features from the data, a process that becomes increasingly challenging as the size and complexity of the dataset grow. Deep learning algorithms, with their ability to automatically learn representations from raw data, thrive on abundance, using the sheer volume of information to uncover subtle relationships and patterns that might elude their more data-frugal counterparts. The availability of large, labeled datasets has been a key driver of deep learning's recent successes. The rise of the internet, with its constant stream of user-generated content, has provided a fertile ground for training data-hungry, deep learning models. Image recognition, for instance, has benefited immensely from vast datasets of labeled images, allowing deep learning algorithms to achieve superhuman accuracy in tasks like object detection and facial recognition. While deep learning's data dependency might seem like a limitation, it is also its strength. By learning from massive, diverse datasets, deep learning models can achieve remarkable generalization capabilities, making accurate predictions or decisions on new, unseen data that differs significantly from their training data. This ability to generalize from large datasets is what makes deep learning particularly well-suited for complex real-world problems, where data is often abundant but messy and unstructured. Another key difference between machine learning and deep learning lies in their approach to feature engineering. In traditional machine learning, feature engineering is often a manual process, requiring domain expertise. Imagine a skilled artisan meticulously crafting a piece of furniture, carefully selecting the wood, shaping it with precision. Machine learning practitioners spend considerable time engineering features that capture the salient characteristics of the data. This process can involve tasks like normalization, standardization, one-hot encoding, and feature scaling. While feature engineering can be time-consuming, it is crucial for achieving good performance with machine learning algorithms. Deep learning, in contrast, automates the feature extraction process. Deep neural networks learn to extract increasingly abstract and meaningful features from raw data without explicit instructions. This ability to automatically learn representations from data is one of deep learning's most significant advantages. Imagine a deep learning algorithm as a master chef, transforming raw ingredients into a culinary masterpiece without a recipe. The network's hidden layers act like culinary stages, refining and transforming the data into a more sophisticated representation. This automated feature extraction saves time and effort and often leads to superior performance. Deep learning models can uncover subtle patterns and relationships within data that might elude human engineers. The computational demands of machine learning and deep learning differ significantly. Machine learning algorithms can often be trained effectively on standard CPUs. Imagine a team of skilled workers, each performing a specific task efficiently. Deep learning algorithms are computationally intensive, requiring specialized hardware like GPUs or TPUs. Think of these specialized processors as teams of highly specialized experts working in parallel. GPUs excel at parallel processing, making them well-suited for training deep neural networks. TPUs, custom designed by Google, enable even faster training times and handling larger datasets. The availability of powerful and affordable GPUs has been a key enabler of deep learning's recent progress. Cloud computing platforms have democratized access to these computational resources. The time required to train a machine learning or deep learning model varies significantly. Machine learning models, generally simpler in architecture, often train relatively quickly. Imagine a small team of agile athletes, completing a sprint in record time. Deep learning models can take significantly longer to train, sometimes ranging from hours to weeks. Think of a team of marathon runners, pacing themselves strategically to cover a vast distance. This difference in training time reflects the trade-off between speed and sophistication. Machine learning models might not achieve the same level of accuracy or generalization as deep learning models. Deep learning models often result in higher accuracy and better generalization. The choice between a faster training machine learning model and a more computationally demanding deep learning model depends on the specific requirements. For tasks where speed is paramount, a simpler machine learning model might be preferable. For applications where accuracy and generalization are crucial, deep learning models are often justified by the superior performance gains. Machine learning and deep learning have both found widespread adoption across a wide range of industries. Machine learning has become an integral part of many everyday applications, from personalized recommendations to medical diagnosis. Imagine machine learning as a versatile toolkit, empowering businesses to optimize their operations. E-commerce platforms like Amazon and Netflix rely heavily on machine learning algorithms to personalize product recommendations. Financial institutions leverage machine learning to detect fraudulent transactions. Deep learning has fueled breakthroughs in artificial intelligence, enabling applications like self-driving cars. Self-driving cars rely heavily on deep learning algorithms to perceive their surroundings and make real-time driving decisions. In healthcare, deep learning is revolutionizing medical imaging, enabling more accurate diagnosis of diseases. Deep learning algorithms can analyze medical images with remarkable accuracy, assisting radiologists in identifying subtle anomalies. Personalized recommendations have emerged as a crucial tool for businesses seeking to enhance customer experiences. Machine learning plays a pivotal role in powering these sophisticated recommendation engines. Imagine browsing your favorite online retailer and being greeted with a curated selection of products. This level of personalization is made possible by machine learning algorithms that analyze your browsing history and purchase history. These algorithms excel at identifying patterns and correlations in user behavior. For example, a recommendation engine might discover that users who purchase a particular brand of coffee often also buy a specific type of coffee filter. By surfacing such hidden connections, machine learning enables businesses to provide more relevant recommendations. The impact of personalized recommendations extends far beyond e-commerce. Streaming services like Netflix and Spotify rely heavily on machine learning to curate personalized playlists. News aggregators leverage machine learning to personalize news feeds, prioritizing articles that resonate with each user's interests. Machine learning has emerged as a critical line of defense in the fight against fraud. Imagine a machine learning algorithm standing guard over millions of credit card transactions. These algorithms excel at identifying anomalies that might escape human detection. Machine learning-powered fraud detection systems operate by learning from historical data. An algorithm might learn that transactions made during certain hours or from specific IP addresses are more likely to be fraudulent. By continuously analyzing new transactions in real time, these systems can flag suspicious activities. The benefits of machine learning and fraud detection are manifold. By automating the detection process, these systems can analyze vast volumes of transactions with remarkable speed and accuracy. This real-time detection capability is crucial for minimizing financial losses. Machine learning models can continuously adapt to evolving fraud tactics, learning from new patterns of fraudulent activity to stay ahead of the curve. Machine learning is revolutionizing the healthcare industry. From analyzing medical images to predicting patient outcomes, machine learning is transforming healthcare. Imagine a world where medical diagnoses are faster, more accurate, and tailored to each patient's unique genetic makeup. Machine learning is making this vision a reality, enabling doctors to analyze medical images with unprecedented precision. Beyond medical imaging, machine learning is being used to predict patient outcomes and develop personalized treatment plans. By analyzing vast datasets of patient data, these algorithms can uncover hidden patterns. The transformative potential of machine learning in healthcare extends far beyond diagnosis and treatment. Researchers are leveraging machine learning to accelerate drug discovery. machine learning is also being used to optimize hospital operations, improving patient flow, and reducing wait times. Deep learning has emerged as a cornerstone of autonomous vehicle technology. Imagine a world where cars can see, interpret, and react to their surroundings with a level of sophistication that rivals human drivers. At the heart of these self-driving systems lie deep neural networks, trained on massive data sets of driving scenarios. These networks learn to perceive the environment through a suite of sensors including cameras, LiDAR, radar, and ultrasonic sensors. The data from these sensors is fed into the deep learning models, which process the information and make decisions about steering, acceleration, braking, and lane changes. One of the key challenges in autonomous driving is object detection and tracking. Deep learning excels at this task, enabling self-driving cars to accurately perceive their surroundings. Convolutional neural networks are particularly well suited for this task, learning to recognize objects from images captured by the car's cameras. Beyond object detection, deep learning also plays a crucial role in path planning. Recurrent neural networks are often used for path planning, taking into account the car's current location, destination, road conditions, and traffic flow. Deep learning has revolutionized natural language processing. From voice-activated virtual assistants to chatbots, deep learning is transforming the way we interact with technology. Imagine speaking to your smartphone as you would to a personal assistant. This level of seamless voice interaction is made possible by deep learning models that excel at speech recognition and natural language understanding. Speech recognition has seen significant advancements thanks to deep learning. Recurrent neural networks have proven highly effective at processing the sequential nature of speech. Once the speech is converted into text, deep learning models are used to understand the meaning and intent behind the user's words. These models can identify entities, extract relationships, and infer context, allowing them to provide relevant responses and engage in simple conversations. Deep learning is blurring the lines between human and machine creativity, enabling the creation of art, music, and literature that pushes the boundaries of artistic expression. Imagine a world where algorithms can compose symphonies, paint masterpieces, and write poems, not as mere imitations of human creativity, but as expressions of their own unique style and imagination. Generative adversarial networks, a class of deep learning models, have emerged as powerful tools for AI-generated art. GANs consist of two competing neural networks, a generator network that creates new data instances such as images or music, and a discriminator network that evaluates the authenticity of the generated data, trying to distinguish it from real data. These two networks engage in a creative tug-of-war, with the generator striving to create increasingly realistic data to fool the discriminator, and the discriminator becoming more adept at detecting fakes. This adversarial process drives both networks to improve, resulting in the generation of highly realistic and often surreal art, music, and literature. The implications of deep learning for artistic expression are profound, raising questions about the nature of creativity, the role of the artist, and the future of art itself. While some view AI-generated art as a threat to human creativity, others see it as a powerful new tool for artistic exploration, collaboration, and innovation, opening up new avenues for creative expression and challenging traditional notions of what it means to be an artist. The fields of machine learning and deep learning, though interconnected, offer distinct paths within the broader landscape of artificial intelligence. Choosing the right path depends on your interests, career aspirations, and the specific problems you're passionate about solving. Imagine embarking on a journey, the destination being a career in AI, but the path you choose will shape the experiences you encounter and the skills you acquire along the way. If you're drawn to the power of data analysis, uncovering hidden patterns and building predictive models, machine learning provides a solid foundation. Think of it as the bedrock upon which you can build a deep understanding of data-driven decision-making. Machine learning equips you with the tools to tackle a wide range of problems, from predicting customer churn to optimizing marketing campaigns and detecting fraud. If you're captivated by the possibilities of artificial intelligence that can perceive, understand, and interact with the world in human-like ways, deep learning offers a challenging yet rewarding path. Imagine yourself at the forefront of AI innovation, developing algorithms that power self-driving cars, create art and music, or translate languages with human-level fluency. The choice between machine learning and deep learning isn't always clear-cut, and there's often overlap between the two. Many deep learning practitioners start their journey with a strong foundation in machine learning principles, as understanding the fundamentals of data pre-processing, model selection, and evaluation is crucial for success in both fields. Machine learning serves as an excellent entry point into the world of AI, providing a solid foundation in data analysis, predictive modeling, and algorithm development. Think of it as a versatile toolkit that equips you with the skills to extract valuable insights from data and build intelligent systems that can automate tasks, make predictions, and improve decision-making. If you're interested in a career path that involves working with structured data such as financial transactions, customer demographics, or sensor readings, machine learning offers a wide range of opportunities. Data analysts, for instance, use machine learning techniques to identify trends, patterns, and anomalies in data, helping businesses understand their customers, optimize their operations, and make better decisions. Machine learning engineers, on the other hand, focus on building, deploying, and maintaining machine learning models that power real-world applications. They work closely with data scientists and software engineers to integrate intelligent systems into existing workflows or develop new applications that leverage the power of machine learning. The demand for skilled machine learning professionals continues to grow across industries as businesses increasingly recognize the transformative potential of data-driven insights. If you're passionate about solving real-world problems, have a strong aptitude for mathematics and statistics, and enjoy working with data, a career in machine learning could be an ideal fit. Deep learning represents the cutting edge of artificial intelligence, pushing the boundaries of what machines can achieve in areas like computer vision, natural language processing, and robotics. If you're drawn to the challenge of building intelligent systems that can perceive, understand, and interact with the world in human-like ways, deep learning offers a challenging yet rewarding path. A career in deep learning often involves working with massive data sets, designing and training complex neural networks, and developing innovative applications that leverage the power of AI. Deep learning engineers, for instance, are in high demand across industries, tasked with building and deploying deep learning models that power applications like self-driving cars, facial recognition systems, and medical image analysis tools. Research scientists in deep learning focus on advancing the state-of-the-art in AI, exploring new architectures, developing novel algorithms, and pushing the boundaries of what's possible with deep learning. They often work in academia or research-intensive industries, contributing to the advancement of AI and its applications. Deep learning is a rapidly evolving field requiring a strong foundation in mathematics, computer science, and a passion for exploring the frontiers of artificial intelligence. If you're driven by curiosity, thrive on solving complex problems, and are excited by the potential of AI to shape the future, a career in deep learning could be an exhilarating journey. Machine learning and deep learning, the twin engines of the AI revolution, are transforming our world at an unprecedented pace, reshaping industries, redefining possibilities, and challenging our very understanding of intelligence itself. From personalized recommendations that anticipate our needs to self-driving cars that navigate our streets, AI is no longer a futuristic fantasy. It's an increasingly integral part of our daily lives. As AI continues to evolve at an exponential rate, we can expect even more transformative applications to emerge, blurring the lines between human and machine capabilities, and ushering in an era of unprecedented innovation and progress. Imagine a world where AI-powered medical devices detect diseases with remarkable accuracy, personalized learning platforms tailor education to individual needs, and smart cities optimize resource allocation and reduce our environmental impact. The AI-powered future holds immense promise, offering solutions to some of humanity's most pressing challenges, from climate change and disease to poverty and inequality. By automating tasks, augmenting human capabilities, and uncovering hidden patterns in data, AI has the potential to unlock new levels of efficiency, productivity, and creativity, driving economic growth, improving quality of life, and fostering a more sustainable and equitable future. However, the rise of AI also presents complex ethical and societal implications that we must carefully consider and address. As machines become increasingly intelligent and autonomous, questions arise about job displacement, algorithmic bias, data privacy, and the very nature of work, creativity, and human connection. Navigating these challenges responsibly and ethically is crucial for ensuring that the AI revolution benefits all of humanity, not just a select few. The AI revolution is not a spectator sport. It's a collective endeavor that demands our active participation, critical thinking, and unwavering commitment to shaping a future where AI serves humanity's best interests. Whether you're a student, a professional, or simply a curious citizen, understanding the fundamentals of AI, its potential benefits, and its potential risks is essential for navigating this transformative era. Educating ourselves and future generations about AI is paramount. We must equip ourselves with the knowledge and skills to thrive in an AI-powered world, fostering critical thinking, problem-solving abilities, and a deep understanding of the ethical implications of AI. By embracing lifelong learning, we can adapt to the changing job market, leverage AI as a tool for innovation, and contribute to shaping a future where AI empowers rather than displaces human potential. As we navigate this uncharted territory, collaboration, open dialogue, and a shared sense of responsibility are more critical than ever. We must foster collaboration between technologists, policymakers, ethicists, and the public to ensure that AI is developed and deployed in a way that aligns with our values, respects our rights, and benefits all members of society. The AI revolution is upon us, and its impact will be profound. By embracing a future-oriented mindset, fostering a deep understanding of AI, and working together to address the ethical challenges it presents, we can harness the transformative power of AI to create a more just, equitable, and prosperous future for all.